everyone. This is Miss List, and today we are taking a look at 2.5, which is on Lewis dot diagrams or electron dot diagrams for covalent molecules. So, for those of you that don't know, a Lewis structure is one that shows how the atoms connect to form a molecule. It's named after the guy that came up with this, and that's why we call it a Lewis dot structure or an electron dot structure. A single bond in a Lewis dot structure is going to be one line or a pair of dots. So we can represent it either way. We can represent it as a line between two atoms like that, or we can represent it with two dots. And the two dots can either be horizontal or they can be vertical. But all of these are saying the same thing, and it's that those two electrons are shared between the two atoms. A double bond means that 4 electrons are shared. And so in a double bond, we would have 4 electrons being shared between the two atoms, because remember, a covalent bond, that's what a covalent bond is the sharing of electrons. So the double bond is going to give us 4 shared electrons, and a triple bond is going to give us 6 shared electrons. And down here is kind of the difference we can see in these diagrams, where we have an example of a single covalent bond, a double covalent bond, the 2 lines. Again, that means that there are 4 electrons there, and sometimes it can be drawn like this instead of the 2 lines. And then the triple bond means that 6 electrons are being shared. And again, if you were going to show that 6 electrons were going to be shared, you can also draw it like this with the dots. Now, these extra electrons that are here on the oxygen and in this one on the oxygen, those are called lone pair electrons. And those are ones that are not bonding. So they are not involved in the bond at all, which is part of the reason why a lot of chemists prefer using the line to show bonded electrons, and then they'll use dots for the lone pair electrons, so the non-bonding electrons. Now, how do we construct these diagrams? There might be more than one correct way to draw a structure. One thing to keep in mind is that we'll figure out how to determine what is the best version in section 2.6. So that's coming, but just keep in mind there is more than one way usually that we can connect these. But to start out, the first thing that we would do is we would determine the total number of valence electrons in an atom. Then I'm going to put the atom that needs to make the most bond to fill its octet. This is usually going to be the least electronegative element. That is going to go in the center. And then I'm going to place all the remaining atoms connected using single bonds. Hydrogen and halogens, they're never going to be the central atom. That's something that we'll learn as we practice. And if we run out of electrons before fulfilling the octets, only then will we consider a double bond or a triple bond. So I think the easiest way to learn this is to just work through some examples. So in this first example, we have carbon dioxide. And the first thing I'm going to do is I'm going to add up my valence electrons. Carbon gives us 4, oxygen gives me 6, and I have 2 of the oxygens. So altogether, I have 16 valence electrons to work with. That means I have 16 total electrons to make all of these connect together. Who goes in the middle? Well, carbon is less electronegative, and carbon needs 4 bonds. So I'm going to put carbon in the middle. And what I'm going to do is I'm going to connect each oxygen by using a single bond. And I'm going to put 1 on each side. Now, remember, each of these lines counts for 2 electrons. So out of my 16 that I had available, I've used 2 to connect here and 2 to connect here. So I've used 4. That means I have 12 left. And so what I'm going to do is I'm going to put those around the outside. So I've used 2, 4. Here's 6, 8, 10, 12, 14, and 16. At this point, we want to check to see if there are octets, so that every atom that needs an octet has an octet. The oxygens do have an octet. They're sharing the 2, represented by this line here, and then they've got 6 lone pair electrons. So they have 8. Same thing for this oxygen over here on the left. We're sharing 2, and then it has 6. The atom that doesn't have an octet is carbon. And so this is where rule number 4 comes in. I can't add any more electrons. That's a common misconception, as students just want to add more dots in, or they would just want to add more lines, and I can't because I only had 16 to work with. So what I can do, though, is rearrange the atoms that I already have. What I can do, though, is rearrange the electrons that I already have. So what I can do is, instead of taking these guys and putting them as a lone pair, I can actually move them in and make a double bond here. So that means that they are no longer up here, and I've created a double bond. Now, that helps me a little bit. Carbon now has 2, 4, 6 electrons, all being shared. Well, if I did that on one side, I bet I could do the same thing on the other side and move those 2 electrons in and make 2 double bonds. If I do that, then I still have only used my 16 that I have available, but now carbon has an octet. So carbon in the middle, it's sharing 2, 4, 6, 8 on each side. Each of the oxygens also have octets. I've still only used my 16, so this is an example of a correctly drawn Lewis structure. Now, I mentioned that there are more than one way to draw some of these Lewis structures, and so a question that I often get asked is, when we were here and we were trying to make octets, we took 2 of those dots and moved them in and made a double bond. Well, I did 1 double bond on each side. And a common question that students ask is, why can't I just take 2 more from this oxygen and make a triple bond there? I've still only used my 16 electrons, and everyone has an octet now. We're going to find out in the next section that there is actually a preferred dot structure. This technically is not wrong, this guy. However, it is not going to be a preferred structure, and that's because of something called formal charge, and we are going to look at that in the next section. So this is the one that I would accept for CO2. All right, let's look at our next example. In our next example, we have HCN. So step 1 is to always add up my valence electrons. I have 1 for hydrogen, 4 for carbon, and 5 for nitrogen, so I have 10 altogether here. Hydrogen never goes in the middle. It is always going to be on the outside. So what I have to decide is who is least electronegative that goes in the middle, or which one has more bonds than it needs to fill octets. And that's going to be our friend carbon. So I'm going to connect using single bonds, the hydrogen on one side and the nitrogen on the other side. So out of my 10, I've used 2 to connect H and C and 2 to connect C and N. So I only have 6 left. So I'm going to start putting the electrons around the outside. So 2, 4, here's 6, 8, and 10. Hydrogen, not only does it go on the outside, but it only needs 2 electrons. Remember, hydrogen is 1s1, so if it gains that electron or shares it, it has a full shell, it's just at 1s2. So hydrogen doesn't need an octet. That's why I put all my electrons on nitrogen. Now, the problem is, though, carbon does not have an octet. So I am going to need to do some rearranging here because I've used my 10 electrons, but I have only made an octet for nitrogen. Carbon does not have one. So similar to what we did in the last example, I'm going to take 2, instead of making them a lone pair, I'm going to move them in and make a double bond. That helps me out a little bit but carbon still does not have an octet. It has 2, 4, 6 around it. And so I'm going to need to do that a second time. So I am going to take 2 more of the valence electrons and move them in and actually make a triple bond. So I've still only used my 10 electrons. I've got 2, 4, 6 in the triple bond. 7 and 8 are over here as lone pairs on nitrogen. And then I have the 2 that are connecting the hydrogen in there. So I've only used my 10. Everyone has an octet that needs an octet. So that is a correctly drawn dot structure. Final example, we have NCl3. Nitrogen has 5 valence electrons, and each of the chlorines have 7 valence electrons. So altogether, I have 26 valence electrons to work with. Nitrogen is going to go in the middle because it is the least electronegative and it has the most electrons needed to fill its octet. And then I'm going to connect the chlorines going around the outside. So I have used 6 just to connect everyone. So I have 20 left over. So if I've used 6 to connect, this would be 8, 10, and 12. This would be 14, 16, 18. This would be 20, 22, 24. And so that last set of electrons is actually going to go on nitrogen. Remember, I only am going to make a double bond or triple bond if I run out of electrons. And in this example, I didn't run out of electrons. So those last 2 electrons can go on nitrogen to make its octet. Everyone has an octet. I've only used my 26 electrons, so this one is good to go. Now, there are some exceptions to the octet rule. Boron is okay only having 6 electrons around it instead of having 8. So oftentimes we might see something like only 3 bonds around boron, something like this. So boron is a notable exception that is allowed to have fewer than an octet. And then we also have some atoms that can do expanded octets. So some expanded octet that are common that show up are phosphorus. Phosphorus can have 10 electrons around it instead of 8. Sulfur can have 12 electrons around it, and iodine commonly can have 14. Now you might be asking yourself, why can these have more than 8? And it's because they all have a d orbital available, and that's what allows for the expanded octet. Let's look at a few examples. These are common to the types of examples that you might see at the AP level. On number 1, they want us to complete the dot structure of ethanol by drawing in all the electron pairs. Now, they have done a lot of the work for you. Notice that they've done a skeleton of how it gets connected. We're still going to follow our steps though. So step 1 is to add up our valence electrons. So each hydrogen gives me 1 valence electron. And since there's 6 hydrogens, that gives me 6. I have 2 carbons, and each of those give me 4 valence electrons. And then I have 1 oxygen that gives me 6. So total, I have 12 and 12, or excuse me, 6 and 6 is 12, and then 8. So I have 20 valence electrons to make this happen. Step 2 is to connect everyone using single bonds. So I'm going to count my electrons as I do them. I have 2, 4, 6, 8, 10, 12, 14, and 16. So I've used 16 electrons just to connect everyone. I have 4 electrons left over. And the question is where do they go? Well, everyone has an octet that needs one. Remember, hydrogen does not need an octet. The carbons already have an octet with 4 bonds around them. That means that those extra electrons I have are going to go as lone pair electrons on oxygen, because oxygen does not have an octet yet. So remember, we only utilize a double bond or triple bond if necessary. In this next example, it says shown below are the Lewis dot structures for propane and methanoic acid. And then they want us to draw the dot structure for propanoic acid. I think what they want us to do is to combine these into two. So propane has 3 carbons in it. So that's where the prop comes from in this example. So I'm still going to have 3 carbons, but then the oic acid is this part. This is what's called a carboxylic acid. And so what we're going to end up doing is to combine them together. Carbon and carbon, and then off of the carbon, I'm going to have the last carbon, I'm going to have this double bonded oxygen with another oxygen next door to it with an H connected to it. And then the rest of the hydrogens are going to go here around my carbons. So let's see if it matches the numbers for the formula they give me. I should have 6 H's. 1, 2, 3, 4, 5. 6 H's. I should have 3 carbons. 1, 2, 3. And I should have 2 oxygens. Does everyone have an octet? Yes. On that example, I did not follow the steps like we outlined them because we were taking 2 pictures and mashing them together. So I didn't really feel it was necessary to go through the drawing of the dot structures for that one. On number 3 here, they want us to draw a dot diagram for methanoate and then the methanoate. In this example, for methanoate, we have 2 hydrogens, each give 1 valence electron. I have carbon, carbon gives me 4, and each oxygen gives me 6. So I have 12, 16, 12 plus 4 is 16, 17, 18. I have 18 valence electrons to make this happen. So who's going to go in the middle? Oxygen is going to go in the, or excuse me, carbon's going to go in the middle. It has the most bonds needed and it's the least electronegative. I'm going to connect a oxygen and an oxygen. I am also going to connect a hydrogen here, and initially I'm going to connect a hydrogen here. So out of my 18, I've used 2, 4, 6, 8. That means I have 9, 10, 11, 12, 13, 14, and then 15, 16, 17, 18. The problem we have here is that this oxygen does not have an octet. And so we need to do some rearranging here. One thing that we can do is to make a double bond, but just making a double bond and by moving these guys in here is not going to necessarily help me because I'll still have less than an octet. What if I just moved this whole guy over and had it connect on this side? So that's what I'm going to do. I'm actually going to just move the hydrogen and have it connect here. That's going to give me an octet on that carbon or on the oxygen. Now you might be thinking, but now carbon doesn't have an octet. Well, that can be easily fixed by creating a double bond here by moving 2 electrons in and making a double bond. So that's what I'll do. I'll move 2 electrons in and make a double bond there. So I've only used my 18. Everyone has an octet that needs one. And that is an example of methanoate. Now they want us to do the methanoate ion. And we haven't done an example of an ion yet. For an ion, we first add up the electrons. I have 1 carbon in this one, 4 for the, or sorry, 1 hydrogen, 4 for the carbon. And I have 2 oxygens each that give me 6. Well, 6 and 6 is 12, 16. That gives me 17 valence electrons. Hopefully by now you notice that the electrons usually go in pairs. So having 17 electrons is a little bit weird, which is why we have this negative charge. Remember, a negative charge on an atom or an ion means that it has gained 1 electron. I actually get to add 1 more, and I actually have 18. So this is going to be very similar, except the difference is we only have 1 hydrogen. So I have connected everyone, 2, 4, 6. So here is 8, 10, 12, 14, 16, 18. I've used all my 18 electrons. Carbon does not have an octet, so I need to take one of those and create a double bond. I'm going to take 2 electrons in and create a double bond there in the middle. Final example is like number 1 in that they give us what's called a skeleton, and we're just connecting how all of this looks. So I see 5 hydrogens, each give 1 valence electron. Carbon gives me 4, and nitrogen gives me 5. So altogether, I have 14 valence electrons to work with. Connect everyone using single bonds. Remember, a single bond is 2 shared electrons. So I have used, out of my 14, 2, 4, 6, 8, 10, 12. So I've already used 12 electrons, which means I only have 2 left over. Which atom does not have an octet? And that's going to be nitrogen. So I'm going to put those 2 extra electrons there on nitrogen. So getting better at Lewis dot structures just takes a lot of practice, which I hope you're getting in class. But that is 2.5, Lewis dot structures for covalent compounds.